Good afternoon, ladies and gentlemen. My name is Nguyễn Phan Khánh Hà from Viettel Research and Development Institute, Viettel Group, Hanoi, Vietnam. Due to some reasons, I could not be attend the conference. Therefore, I would like to present our research entitled Classifications of Pulse Repetition Interval Modulations using Neural Network via this video. Is what I'm going to talk today. Firstly, I will introduce the pulse repetition interval classification problem, the reason why we should consider this problem, and why it is not a trivial problem, and briefly review related works. Secondly, I will describe in detail our proposed scheme and show some achieved result. Finally, some conclusion and future works will be shown. As you can see in this figure below, pulse repetition interval is defined as the distance between times of arrival of consecutive radar pulses. This is an important feature of a radar signal. Therefore, classification of PRI modulation is the foundation to identify emitting radars. This is one of the essential signal analysis operation of electronic intelligence system. However, this is not an easy problem. Classifications of PRI modulations face multiple challenges. First, nowadays, modern radars use various complicated types of PRI modulation, such as sliding up, sliding down, the well switch, structures, and so on, with diverse PI parameters instead of simple types such as constant PI or Chester PI used in classical radars. Second, received radar pulses sequence usually suffer unavoidable perturbations, misdetections, and false alarm. These unexpected noises result in a noisy input PI sequence, making the recognition task much more challenging. As you can see in this figure below, in the left-hand side, with noise-free PI input sequence, it is very easy to recognize different types of PI modulation. However, in case of noisy PI sequence, it's very difficult for us to classify different types of PI modulation. Before showing the detail of our proposed scheme, I would like to briefly summarize a related study to show the PI modulation classification problem. Existing methods can generally be divided into four categories. First, in histogram-based scheme, PI modulation types are determined by the difference TOA histogram. Second, PI transform-based scheme define a complex autocorrelation function of radar pulse TOA sequence to find the PI. However, both histogram-based and PI transform-based scheme can work well with only simple types of PI modulations, such as constant or jitter, and their recognition accuracies decrease significantly with very noisy input PI sequences. Recently, there are many active works using a decision tree with extracted features from PI sequence. Although these methods achieve a quite good classification performance, it requires heavily handcrafted thresholds, which are very sensitive to noise and to the change of PI parameters. Last but not least, learning-based methods, for example, using SVM or neural network, is another efficient approach for solving these issues. Now, let us continue with the description of our proposed scheme. To solve the problem, given a sequence of radar pulses with corresponding TOAs, how to automatically recognize PI modulations of radar signal. We propose a new learning-based method called feature-based neural network (FNN) to classify 7 types of PI modulation, as indicated in the previous slide, such as constant, jitter, sliding up, sliding down, the well switch, starches, and globulated PI modulation. Our methods contain 3 main phases: the pre-processing, the features extractions, and the classification. In the pre-processing phase, a noisy input PI sequence is filtered to remove unwanted noise. Next, 6 features are extracted from pre-processed PI sequence in the features extraction phase. These features are the input of a feed-forward neural network in the third phase to automatically recognize PI modulation of radar signal. Next, I would like to show you more detail about 3 phases of our. In the pre-processing phase, a noisy PI sequence is filtered using a median filter with window size is 2K plus 1. As you can see in the figure, since the perturbations, misdetections, and false alarm of a radar pulses result in a PI sequence with spectral noise, median filters is an efficient tool to mitigate the effects of this type of noise on PI sequence. And the right hand side show that median filter is very effective tool to remove and to mitigate the effect of noise on PI sequence. Following the pre-processing phase, in the feature extraction phase, 6 features which characterize different PI modulation types are extracted from pre-processed PI sequence. Based on the autocorrelation functions of PI sequence shown in this formula, 2 first features are derived. Feature 1 measure the variation of PI sequence with respect to its average value. In this formula, Vp is the average values of PI sequence. Thus, this feature distinguishes constant PI with least variation from other types of PI modulations. The second feature based on the autocorrelation functions is the ratios of lag 1 and lag 0 autocorrelation values. Generally, with starches PI, this ratio is much higher than those of other PI modulation. The third feature is obtained from the number of PI cluster. Using this formula, to evaluate the number of PI cluster, first, the PI sequence is sorted in ascending order. Then, based on this sorted sequence, if the difference between 2 consecutive PI values is greater than a predefined threshold T, they are separated into 2 different PI clusters. The number of PI cluster is an excellent feature for discriminating starches and the well switch PI, which has multiple discrete levels of PI from the rest. Three remaining features of PI modulations are adopted directly from the study in reference 9, shown here. To deduce the features, a symbolization technique is used. The symbolization technique transforms a time series data into a symbol sequence and then carry out quantitative statistic analysis on this symbol sequence. This is a very useful tool for time series analysis, since by analyzing symbol sequence, we can easily find out unique information to distinguish patterns in original time series data. The process of feature extractions based on symbolization is as follows. First, we symbolize PI sequence and the difference of PI we call DPI sequence to create it two corresponding code series called CPN and CDN. Next, based on the code series, three features will be extracted. Let us consider an illustration of symbolization PI sequence as shown in the example in the figure in the right hand side here. The PI sequence is mapped to a symbol series according to a partition rule indicated in this formula. Here, VP is the mean value of PI sequence. We can see that by using this partition rule, we map the PI sequence to a binary symbol series containing 0 and 1 value. From symbol sequence, code series CPN is calculated with the number of symbol is 2 and the sequence length is 3. Using this formula, it is clear that the range of code series CPN is from 0 to 7. And similar to symbolization of PI sequence, the symbolization of DPI sequence starts from mapping DPI sequence to symbol series by a specific partition rule indicated in this formula. Then, code series of DPI and sequence CDN is calculated using this formula with the number of symbol is 3 and the sequence length is also 3. Thus, the range of this code series vary from 0 to 26. After the symbolization process, you can see that three features are acquired from code series. The feature 4 is the normalized entropies of histogram of code series CPN using this formula. Due to the randomness of PI values, the entropies of jitter PI is normally largest, that means closest to 1, compared with other types of PI modulations. The next feature is the kurtosis of code series CDN, the code series of DPI. Kurtosis is a very common metric used in statistics to quantify the sharpness of a probability function distribution. Because the code series CDN of globulated PI modulations usually has dispersed distribution, its kurtosis is relatively small compared with others. Thus, this is a good characteristic to discriminate globulated PI modulation from other PI types. The last feature is the normalized second-order sample moment of code series CDN. This is an outstanding feature for the classification among sliding down the well switch and sliding up PI, which have the features value of approximately 0, 0.25, and 1 respectively in case of noise-free. After the feature extraction phase, 6 features are the input of a feed-forward neural network to classify different PI types. The structures of our proposed feed-forward neural network is shown in this figure. The proposed neural network consists of 4 layers: an input layer, a fully connected layer of length 6, a softmax layer of length 7, and finally an output layer of length 7. The output of the neural network is a probability function vector of length 7 corresponding to 7 PI modulation type. The recognized PI type is selected as position that has the maximum value in this output probability vector. Now, I would like to turn to the performance evaluation section. The simulated PI modulation parameters are shown in the table. We have some common parameters for all types of PI modulation, and for each PI modulation we have some specific config parameters. We consider the maximum missing pulse and spurious pulse rate is 10%, and the maximum PI perturbation is 1 microsecond. To train our neural network, 1400,000 randomly generated PI sequences are used. That means 20,000 for each type PI modulation. Then we use 35,000 random PI sequences, different weight training sequences, to verify the accuracy of our classifier. To evaluate the performance of our proposed scheme, called FNN, we compare FNN with two of the state-of-the-art methods. The first one, named SDT, stands for Symbolization-Based Decision Trees, is the decision tree-based scheme proposed in reference 9. It should be noted that this method is able to classify only 5 different PI patterns compared with 7 types PI modulations of ours. The second one is a learning-based scheme proposed in reference 10, which the input of neural network is the different PI sequence. So we refer these methods as TNN, stand for Transform-Based Neural Network. The figure here shows the confusion matrix for 3 aforementioned schemes. Among schemes, our proposed scheme achieved the outstanding classification accuracies of 99.59% in testing sets compared to 90.81% of SDT and only 65.92% of TNN. Before finishing my presentation today, I would like to take a minute to wrap things up. In this paper, we propose a new learning-based scheme using input features to recognize efficiently 7 types of PI modulation. The simulation results show that our proposed scheme outperforms other classifiers in terms of classification accuracies. In the future, we will investigate a deep learning approach to solve the PI modulation classification problem. That means we take raw PI sequence as the input of neural network instead of features. Here are some references used in our paper. And finally, thank you very much for your attention. I would be very happy to answer any questions you might have via the email shown here.